In this lesson, we will give a mathematical semantics of our programming language. By mathematical semantics, we mean a completely precise explanation of how programs execute. Nothing will be hidden. Everything will be clear. This lesson is the most mathematical of all the lessons in this course. Mathematics is the language of precise thinking, and precision is very important. If you do not understand something precisely, then you do not master it, but it masters you. If you know nothing about how a car works, then a car mechanic can tell you whatever he wants and charge you whatever he wants. If you know nothing about arithmetic, then you can't balance your household budget. If you know nothing about government, then you cannot vote wisely and the government becomes a tyranny. If you do not understand the meanings of words and how they are put together, then you can't read a novel. Not only writers have to understand words, but readers too. It's the same with programming. To write correct programs and to understand other people's programs, you have to understand the language deeply, not just superficially. All software developers should reach this level of understanding. The goal of this lesson is to show you how to get there. There are many ways to understand how programs execute. We will present the simplest way that we know of that is able to explain most programming language concepts. Our approach is called an operational semantics because it explains a program in terms of its execution on a machine. We will use a simplified, precisely defined, abstract machine. There are many other approaches to explain what a program does. 3 are particularly widely used. It's axiomatic semantics, denotational semantics, and logical semantics. Let me just introduce them very briefly so you can understand better the range of things that semantics talks about. An axiomatic semantics explains execution as a logical implication. If certain properties hold true before a program's execution, then some other properties hold true after the execution. Denotational semantics explains a program as a function over an abstract domain. Combining programs, where one program is embedded in another, then becomes simple functional composition. Logical semantics explains a program in terms of a model of a set of logical axioms. Program execution is then deduction. It derives true properties from the axioms. All 3 of these approaches that I just mentioned have their uses, but they are all limited in the kinds of language concepts they can explain easily. The operational approach, the one we're going to use, is the most general one because it explains what an execution does, and all programs must execute.